Welcome back to Module 2.2. This module is dedicated to giving a rough overview of the possible algorithms and applications on quantum computers. I will start with some applications of quantum computers, in particular optimization protocols, but also, in the spirit of Feynman, Hamiltonian simulation. Afterwards, I will go through the quantum phase estimation algorithm, which is important in the implementation of these tasks. Let's get started. Optimization protocols are usually referred to as finding the global minimum of a function f of x. For example, assume that we have a function f that depends on binary variables x1 and x2. If x1 and x2 can only take values 0 or 1, then we see that the optimal solution to this problem is either the combination 0, 1 or 1, 0. This is of course a very simple problem, but there are generalizations to these problems called QUBO. QUBO stands for quadratic, unconstrained binary optimization, and can be generally described by the following function. To solve a general problem like this is very hard. So how may quantum computers aid in this situation? In this case, it turns out that by doing a simple substitution like this, the function will take a form that looks like the Ising model, where you can interpret the z operators as spins interacting with strengths Gij between each other and externally with a magnetic field Hi. In this new language, we see that finding the optimum amounts to finding the ground state of this Hamiltonian. These sorts of problems have been tackled by researchers studying adiabatic quantum computing. Near term, it will, however, be difficult to fully utilize the power of quantum computers, and hence many proposals rely on quantum classical algorithms to amount to running a quantum circuit subject to some parameters and then optimizing the outcome via a classical method, for instance gradient descent. One of the biggest applications, however, will be in the realm of quantum simulation, also referred to as Hamiltonian simulation. Simulating the quantum effects of a many-body system is almost by definition harder to accomplish on classical hardware. As we mentioned in the previous module, the number of classical bits required to describe n qubits grows exponentially. Hence, for very large quantum systems, it might be necessary to work on exclusively quantum hardware. For many industrial and medical applications, it becomes very important to be able to predict certain properties of possibly a mixture of many different compounds. For instance, one can describe the Hamiltonian of a system by its kinetic and potential energy. By solving for the ground state, one can infer many properties of the system, like its electrical, mechanical, and optical properties. This brings us to the natural question of how would one even understand the effect of a Hamiltonian on a state? In other words, given some unitary operator u, which encodes some Hamiltonian, how can we determine its eigenvalue theta for a state psi? The quantum phase estimation algorithm makes use of the superposition principle and interference to deal with this problem. Here, you can see the circuit diagram of the algorithm for 2 qubits. The circuit starts off with a qubit in the 0 state, and another qubit psi, of which we want to determine the eigenvalue theta, after applying the unitary u of theta. The algorithm, in layman terms, encodes the eigenvalue theta in the superposition of the first qubit, and then measures it. Skipping some mathematical details, if we measure the overlap with the 0 state, we arrive at an explicit formula relating the eigenvalue with the probability, which enables us to find the ground state of the Hamiltonian by finding the state psi, such that it returns the lowest value of theta. To put it in a nutshell, we saw that with the use of qubits and their properties, we may find new ways to optimize problems and simulate nature at a fundamental level. Of course, there are many more applications that we did not get into, including the HLL algorithm to compute inverses of large matrices, the use of quantum randomness for random number generation, and the entire fields of quantum cryptography and quantum communication. Next time, you will have Kenji talking about CQASM, where you will, in part, also explain how to implement the quantum Fourier transform, which is essential to generalize the quantum phase estimation algorithm for larger qubit systems.